Welcome back. In this video, I discuss the goals of spread control systems and how these systems may miss those goals due to using half-baked infection reproduction models. Countries try to decrease two main variables during a pandemic. First, they target reducing the infection rate, the number of healthy people who become infected. That is why you are asked to frequently wash your hands with soap. They also target the reduction of the mortality rate, the number of infected people who pass away. That is why governments are avidly buying ventilators. The end goal of spread control systems is to reduce infection rate. To reduce the infection rate using spread control systems, first we need to have an accurate model for understanding infection reproduction. Half-baked models can mislead us to develop half-baked solutions. I'll go over two such models in the next slide. What I see is that most simulation models of infection reproduction are based on contacts between individuals. That means if person number one is infected, all his contacts are high-risk carriers. Recall Singapore's contact tracing system that I explained in part 1. In that system, contact is practically defined as having been within 2 meters of another person for 30 minutes. However, we know that the coronavirus stays alive and contagious for hours and even days on surfaces. In one case in China, the pink passenger who was infected did not have any contacts with the red infected passenger. The pink got on the bus 30 minutes after the red got off the bus. This person-to-person infection reproduction model and the system built upon that do not include such contacts between a healthy person and an infected place. Another half-baked model of infection reproduction is based only on person-to-place contacts. In this model, if person number one is infected and is on a bus, the bus is also infected. Therefore, all people who are on that bus or will be on that bus are high-risk carriers until the bus is disinfected. Recall the case of the Chinese checkpoint-based contact tracing system that I explained in part 1. In that system, contact is practically defined as an association between a person and a place. This model works for a bus, perhaps a train or a plane, but not for a big public venue like a university campus or a subway station with thousands of people and airflow. We cannot reliably tell thousands of people that they are high-risk carriers. The accuracy is compromised. Identifying person-to-person contact is also essential. I suggest a model of infection reproduction that combines the two previous models. In this model, exposure occurs through both a person-to-person contact and a person-to-place contact. Now that we have a more reliable infection reproduction model, let's use it to understand countries' responses. To reduce the infection rate, many countries adopted a national lockdown, closing public places and putting restrictions on going outside. It worked. However, the blind national lockdown makes universities, gyms, buses, factories, and farms empty of employees and customers. If it is taken in the long run, it can kill the economy and lead to social unrest and even more death. Therefore, countries try to adopt an intelligent quarantine approach. Infected and high-risk people are asked or legally obliged to self-quarantine. That is, quarantine people are prohibited from leaving the quarantine areas, often their homes, and instructed to maintain a strict separation from family members. The intelligent quarantine approach hinges on increasing exposure awareness rate. the percentage of exposed people who are aware of being exposed. This is quite difficult in the case of COVID-19. Many people and places are exposed without knowing that. Exposed people and places must be identified first so that they self quarantine themselves. Moreover, countries need to increase the quarantine compliance rate. They need to lower the percentage of quarantine violations. This is also quite difficult, as a vast number of people are infected or exposed. Ensuring compliance requires enormous resources that are not available. As a result, violations of quarantine regulation are reported all over the world. The spread control systems help increase both exposure awareness and quarantine compliance rates. But how? Assume that an infection is confirmed. Spread control systems facilitate contact tracing, identifying potentially exposed people and places, the yellow and red circles. They also improve the quarantine compliance rate by reporting violations of quarantine and motivating those people in quarantine to respect the regulations. They can also check entry permission into public places, preventing high-risk individuals from entering public places and infect vast number of people. In summary, the end goal of a spread control systems is to decrease infection rate. The two main goals of these systems are improving exposure awareness and quarantine compliance rates. Exposure awareness rate is improved by means of enabling contact tracing, detecting those who are exposed but unaware of being exposed. Quarantine compliance rate is improved by means of tracking violations of quarantine as well as preventing high-risk individuals from entering public and community places. In the next video, I discuss three types of spread control systems based on the three means goals specified in this video. You can also help with this study. The accuracy of the results of this study will be improved if I receive more quality comments from my peer researchers and health authorities. To increase the number of such comments, the video should be viewed by as many people as possible. You can increase the probability of that by hitting the like button, sharing this video with your network, leaving a comment, and hitting the subscribe button. Thank you for your support. Stay safe.